So today we're going to be looking at exercise 6D, which we're going to cover index laws 4 and 5. So looking at the index laws today, we're mainly going to be examining cases where we have expressions with indices and where we have either division or multiplication within a bracket. And we have our index on the outside of that bracket. And we're going to be looking about how we express it. So looking at index law 4, we're just going to look at the example right now of 2x in brackets squared, right? So we know this is 2 times x, and if we write it out, it's very important to note that this is not going to be equal to 2x squared, right? When we do these things, when we expand these expressions where we have the indices on the outside of brackets and 2 terms multiplied on the inside, we have to write it like this. We have to have 2x in brackets squared, so 2 times x, all the power squared, and we have to square every term within that, right? So we have to square the 2 and the x separately, okay? So if we were writing this out, we'd have to write 2 to the power of 2 times x to the power of 2, which would give us 4x squared. So it's really key that when we're looking at these things, we remember to square every term inside, so both the pronumeral at the front and also any algebraic expressions like x, a, b, y, anything like that, we have to square all of them within it. Okay, so index law 5, very similar. We're just looking at when we have fractions on the inside of brackets. So if we have something like y cubed, right? If we have y on 3, right? Y on 3 in brackets cubed, again, all we have to do is we have to make sure that we square every term. So if we could rewrite this as y times 1 on 3, and if we write this looking at index law 4, we can kind of see how we've made this jump from index law 4 to index law 5, right? Because this is just the same. If we rewrite it like this, we can just say that it's the same as index law 4, where we're just cubing 1 on 3. So it's important that we cube both the denominator and the numerator. So that's one way of writing it. We could also write it as y cubed on 3 cubed, which we would have to do eventually, so just noticing that this is the same as y on 3 cubed, right? So we can just do that, and then we could just say that this is going to be equal to, or maybe possibly should write it the other way just to not confuse anyone. So this is the same as writing y cubed on 3 cubed, because we just bring this in here and we also bring it down here. Whenever it's in on the outside, whenever the index is on the outside of the brackets, we always cube all the terms on the inside. So then we have 3 cubed, which is going to be equal to y cubed on 27, because that's what we have. 3 times 3 times 3, so we get 27. Okay, so this is the same as writing. We could write y cubed, and the reason we do it like this is because we can write y cubed, so y on 3 cubed. This is the same as writing y on 3 times y on 3 times y on 3. And if we look at this, we can see that we're just going to have 3 times y on the numerator. So we're going to have y times y, which is going to be y cubed on the numerator. We're going to have 3 times 3 times 3, which is 3 cubed on the denominator. So that's the logic behind this process, is we are multiplying it. Same with index law 4, 2x squared is going to be equal to 2x times 2x, right? Just make that a little bit clearer for you. That's an x. 2x times 2x, which is going to be the same as 4x squared, because we have the 2 times 2 and the x times the x. So we'll work through a couple of examples here, and then we'll see whether you want any more. So just looking at the 4th index law, now we have something different, right? Now we have -2, right? So when we're looking at this, so example B, we're going to have -2 x cubed y inside the brackets with an index of 4, right? So if we write this out, that's the same as writing -2. Now it's important that we write that -2, because it's not just 2, it's -2 in here. So it's going to be the same as writing -2 to the power of 4 times x cubed to the power of 4 times y to the power of 4, right? And we know that when we have x cubed and we have that to the power of something else, we're just going to multiply these two powers here, right? So multiply these two. And we know that -2, because it's an even power, that's going to become positive, and it is just going to be 2 times 2 times 2 times 2, which is going to be 16. So we'll get positive 16 because it's an even power of a negative number, multiplied by x, where we multiply those two powers, so 3 times 4, so we're going to get x to the power of 12, and then we have that y to the power of 4. Whereas looking at c is going to differ in this way because we have that 4 on the outside. So then we're not going to do 4 to the power of 5 because it's outside the brackets. So in this case we'd have c, and then it'd be the power of 2 times 5, right? And 3 times 5, so we're multiplying those two. So we'd end up with 10 and d to the 15 because we're multiplying those two powers. And we get rid of that 5 because we've just added it to all the terms on the inside, and then that would give us a final expression of 4 c to the 10 d to the 15. Do we have any questions about that so far? No? Fantastic. Okay. Well, let's just look at the fifth index law. So remembering that the fifth index law, we might not go through all of these examples. I'd just like to go through examples B and C because I feel like they're a little bit different from what we've seen so far. So example B, so we won't do this example. You can do that on your own if you feel like it, otherwise I'll leave it there. So we have -3m cubed on 2np squared, all in brackets, to the power of 2. So when we do this, remember it's the same as writing -3m cubed multiplied by -3m cubed on the numerator. So we just bring that 2 in, so it comes in here, and it comes in here. And when we have, we're going to multiply the powers in this case, and we'd actually multiply the powers in the -3 as well, but since the power of -3 is just 1, it just becomes 2. So we would have -3, and remember we have that in brackets because we're squaring the whole thing within it. So -3 to the power of 2 multiplied by m cubed to the power of 2. And then we bring that in. We also have 2 to the power of 2 and n to the power of 2 plus times p squared to the power of 2, which would be equal to, and I'll just make that a little bit more clear because I know my handwriting is getting a little bit small, p squared to the power of 2. We're just going to have that would be equal to, because remember that negative, we have an even power, so it becomes positive. We'd have 9m to the power of 6 on 4n squared p to the power of 4. Yes? So that might be a little bit different from what we're used to because we have multiple terms in both our numerator and denominator. And now we'll just do C, which is going to be, it's fairly straightforward compared to what we've seen already, but now we're going to add in a multiplication as well. So now we're adding multiple index laws. So if we bring that in, looking at it just quickly, going off what we say, we bring that 3 in. So we get x cubed times y to the 6 because we multiply those powers on 2 cubed, which is going to be equal to 8. And we multiply that by x squared on 9y squared. And remember when we add these, when we take this and we expand it further, we're going to need to add those powers on the numerator. Now in this case, when we're multiplying, we'd add the powers of all these things. So we'd add, because there's no y term in this second fraction, we just add the powers of the x. So we get x to the power of 5, because that's 3 plus 2. And then we have y to the power of 6, because we don't have a y term in that numerator of that second fraction. And we put that on 8 times 9y squared, which is equal to x to the power of 5. And then that on y to the power of 6 on 72y squared. Now we know that those, when looking at our divided index laws, now we're just going to look at that and we're going to cancel those two, okay? So we're going to have x to the power of 5, y to the power of 4, because we cancel those two, we subtract those powers on 72, okay? Does that make sense?